I just use it as an occasion to advertise once more the great summer school which we have in July, and I think you still have a chance to participate before we fully booked, and the program is amazing. So well, you can see that we have very prominent researchers as well as very promising young researchers working on very exciting topics, all related to well, general distributed computing agenda, but with some detours to more like popular and fancy fields. Okay. So this is going to be about not about blockchains per se, but about the problem which most blockchains solve. And we are mostly focused on the synchronization requirements imposed by this problem. And the problem is digital currency. And this is joint work with Rashid Galawi, Matteo Monti, Matej Pavlovic, and Adi Serendici from EPFL. So if you look at the original article published by famous Satoshi Nakamoto, where the very term blockchain was introduced. So already in the abstract, the paper says that the main problem they try to face is the problem of double spending of assets. So we have accounts, and we have some owners of the accounts who try to use the same money twice. And the solution they propose is, well, as I say, that the only way to confirm the absence of a transaction, well, is to be aware of all transactions. So you collect all the transactions, you don't have a centralized party, you try to exchange information with each other and try to collect information of all transactions which have been proposed. And then to avoid double spending, the solution they propose is to build a linear order, or build a total order on all these transactions. So everybody agrees in which order this transaction should be executed. And this is exactly what we try to contest here. We say that might not be necessary to agree on the order. But follow-ups of this work, like numerous research articles as well as industrial prototypes, which took this idea and implement this total order in different forms. Yeah? And as we know, or most of us know, that implementing total order in a distributed system requires consensus. Consensus is actually, it's funny that the major industrial conference on digital currency is called consensus, suggesting that consensus is the central building block for solving this problem. Okay. So in this talk we, I will try to convince you that cryptocurrencies do not require consensus. So you can do it easier. Well, one important thing about consensus is that there are no cheap implementations of consensus. Either you pay energy, like if you try to do proof of work consensus, which some people call it, or you spend a lot of communication, a lot of bandwidth to exchange information if you do it in a private context. So we introduced the notion of asset transfer data type, which is somehow abstracts away this cryptocurrency problem. And we show that if the cryptocurrency is defined as K-owned meaning that there are some accounts which might allow up to K owners to debit money from it. Then we show that the consensus number of this data type is exactly K. I will try to define more precisely what consensus number is. And intuitively it means that if you have one owner per account, the consensus number is 1, and specifically it means that you don't need consensus. And then we give, well, this is more like abstract result in the area of concurrent data structures. We treat this abstraction as a concurrent data structure, and then we go to the more realistic setting of message passing systems with Byzantine failures. So in a system in which you have parties which do not trust each other, and they exchange information using message passing. And in this system, we give an asynchronous asset transfer algorithm, and we argue that it's cheaper and less demanding than a consensus-based solution. Okay? And please stop me whenever you have any confusion. So just to recall what consensus is about, before I refute it. So consensus is what we call a one-shot problem. Yeah, everybody comes with an input and expects to get an output. So in this simple case, you have three processes which propose binary inputs, zeros or ones, and at the end of a computation, they need to agree on one of them. Yeah, need to select one of the inputs and achieve perfect agreement on this. Okay. So why consensus? Why it's important to talk about consensus? Because it's a universal abstraction. What does it mean? It means, well, in the concurrent setting with concurrent objects and exchanging information through invoking operations on concurrent objects, we can show that using consensus, well, if we can solve consensus among n processes, we can implement any sequential object. So specifically, it's called universal construction. And actually, this notion is coming from Maurice Herlihy, who was the first speaker today. And it turns out that this is a key to implement a generic fault-tolerant service. Generic in the sense that you just give a sequential specification of the service and make it replicated and fault-tolerant. Just using consensus. Intuitively, you use consensus to agree on the order of operations on this replicated state machine. Well, what we know as blockchain is essentially a replicated state machine. So we agree on the order of events. We can interpret these events as operations on the state of the chain. Well, in the specific case of blockchain, essentially the operation is adding a new transaction to the chain. But like in a more complicated way, it could be a generic program like smart contract. Okay. So this is the question. So what is a cryptocurrency? How do we define it? Well, we take a very simplistic approach, but just to be as general as possible. So we say we have a set of processes, account holders. We have a set of accounts. We have a mapping which maps an account to a subset of processes. So we call them owners of the account. It could be a subset, not necessarily a single owner. And we have a balance map. It's a part of the state of this abstraction. The balance gives the amount of money on each account. Here we talk about fungible coins, but it's not necessary. It's just for simplicity. We could think of non-fungible items, antiquity items or whatever. Okay, there is some initial balance which is known to everybody. On the interface, the abstraction provides two operations. Transfer, naturally, transferring X coins from account A to account B. And the transfer can be successful or not. Successful depending on if you have that amount of money on the account. I'm talking about sequential behavior for the moment. And of course, we need to be able to read the state of the account. We have read operation and the transfer operation. So we call this all the asset transfer data type. So intuitively, we don't need total order if you want to implement this thing in a concurrent environment, because, well, many operations commute. For example, if we consider a specific execution in which you have 4 players and 3 transactions. Bob wants to transfer $100 to Alice. Drake wants to transfer $100 to Alice. Alice transfers $100 to Carol, and let's say Alice had an empty account initially, and the transfer T0 depends on T1. Depends in the sense that Alice first received money from Bob and then transferred this money to Drake. So there is some causality between these two transactions. If this causality is observed, we can say that T2 does not matter where you put T2. T2 can either be ordered before T1 or after T1 and before T0 or after T0. It does not matter for the success of the operation, assuming that Drake has enough money to transfer out. So we have a partial order. So not necessarily total order. What does it mean partial order in the distributed systems? It means that as long as you respect this partial order, you can locally, in your local copy of the state of this abstraction, you can execute transactions arbitrarily. Okay? We somehow suggest that total order is not necessary, and indeed, we can actually show that. Well, let me first define what consensus number is. So consensus number for a concurrent data structure is this maximal number of processes that can solve consensus using this abstraction, using this object. So it's a maximum number of processes that can be synchronized perfectly using copies of this object and well, some read-write registers. And we always assume that you have some ability of reliably communicating with each other. Yeah, well, there is this notion of consensus hierarchy, also thanks to Maurice Herlihy, where we say, what does it mean that one concurrent data structure is stronger than the other? Okay. Yeah. It means that one of the way of measuring the power of a concurrent object is to define its consensus number. If one object has consensus number k and the other one is k minus 1, then we intuitively say that one object is stronger than the other. Oh. Very roughly. Yeah, there is a whole hierarchy, and actually, well, some objects have consensus number infinity because they can be used to synchronize any number of processes. And the abstract compare and swap instruction is very powerful. Okay. So first result, we say that in a single owner case, when you have one owner per account, the consensus number of an asset transfer type is 1. And here is a very simple algorithm based on snapshots. And we know that snapshots can be implemented with read-write. So using just read-write communication, we can solve this problem. And as I said, the read-write registers have consensus number 1. Whatever you can implement with read-write registers has also consensus number 1. It cannot be 2. And here's an algorithm. So in an algorithm, you just publish your transfer, take a snapshot, and apply the transfer to the snapshot and compute the result. So very, very, very simple. To read, you just take a snapshot and compute the balance of the account you're interested in. So this is, and actually you can generalize it quite easily using some restricted scope universal constructions using k consensus objects, k process consensus objects. You can say that for k owner case, you can easily show that the k owner case asset data type has consensus power exactly k. So if you have k owners per account, you have to be able to solve consensus among k, but probably not more. And in practice, it matters a lot because it's much easier to synchronize smaller number of processes than the whole system. You don't need to achieve the total order. You need some kind of partial order, and you need total order among the owners, but not among everybody. Okay. Well, this was all for what we call a benign case. So the notion of consensus number is defined for the system where you have just benign behaviors, like you give protocols to processes and they behave. Well, they respect the protocol, except that they can fail by crashing. They can stop prematurely. That's this consensus hierarchy is built for what we call weight-free systems, weight-free protocols. Well, in the world of digital currency, it's too optimistic. We assume systems where we have mutual mistrust. Processes can deviate from the protocol. They can behave selfishly. And for example, they can try to double spend. So what is double spending in this with respect to this abstraction? And in this case, for example, we have again 3 transactions for 4 users. In this case, Alice wants to issue 2 conflicting transactions. It wants to issue 2 transactions using the same money which she received from Bob. So how we exclude this? I mean, specifically, it means that there are 2 causality chains or 2 causality arrows here, but they conflict. They cannot be married in the same system. They don't respect any kind of sequential behavior of the whole set of accounts. And intuition here is that how we do it, how we avoid it without consensus. The intuition here is that instead of consensus, we can use what we call a secure broadcast. Essentially, we don't care if everybody agrees on the order of these 3 transactions, T0, T1, and T2. What we care about is that Alice cannot lie about its causal past. If it says, I used T0 to transfer money through transaction T1, I cannot say someone else that I used T0 for transaction T2. In fact, this is some kind of problem which has been solved long ago. And this is a problem, in the one-shot case, it was introduced by Braha like in 1987. This was called, I think, Byzantine Broadcast or Byzantine Agreement. And then it was extended to the long-lived case, multiple shot case by Malkin Writer. And it's a broadcast which in addition to classical broadcast properties like reliability and so on, no duplication, no creation, has the source order property. Source order means that your message is coming from the same source, even if the source is Byzantine, or are delivered in the same order. Okay, so we don't care about the global total order. We care about source order. And in fact, this is exactly what we need for this kind of problems. So again, these are there are protocols designed for a private setting, or a setting where you know everybody, and Byzantine bounded number of Byzantine failures. Well, as usual, we assume that you have less than 1/3 of Byzantine failures. You cannot do it without it, and then we can implement it. And in fact, with the algorithm which we built, it uses the secure broadcast as a black box. And this is a big advantage, as we'll see in a minute. So in fact, what we have on the top level of the algorithm is just some causal path tracking. So we just make sure that every message which you send is provided with a causal path. Yeah, this is but how you send messages using secure broadcast. Yeah, so this is, and you use the standard interface for that. And in the private case, we have a deterministic solution. And we just use the algorithm by multi-writer, essentially. And the intuition here is just, you deliver the message only if you have a certificate from sufficiently many processes, or a quorum, or a Byzantine quorum of processes. Say, we can accept this message. And intuitively, you cannot double spend because every two Byzantine quorums intersect on one correct process, which cannot lie. Should say, if I accepted this one, I cannot accept the other one. Okay. But the advantage of this modular approach is that we don't have to restrict ourselves to the deterministic protocol. We can use a probabilistic one. And probabilistic one, this is another contribution, which is under submission now. I shouldn't talk too much about this, but intuitively, it's something which can be used in a public environment. So in an environment where you don't necessarily know every participant, you don't have strong identities. Yeah, you have some Sybil attacks or something. And instead of providing strong guarantees using quorums, intersecting quorums in a Byzantine system, you give probabilistic guarantees using samples, much smaller subsets of members which you know, and you communicate through them using some epidemic broadcast, gossip-based probabilistic broadcast. Yeah. The difficulty here is not the protocol itself. The protocols are very simple. You have a number of rounds using some weighted samples in your system. The difficulty is the analysis. So it's usually very difficult to analyze probabilistic protocols and give you bounds on the security of your resulting algorithm. But one of the contributions of this work is actually building these bounds and showing that the bounds are tolerable, so not crazy bounds which you never can achieve. I very briefly go through this. So it's not very surprising, but if you take like the best of known BFT protocol, like an algorithm which implements a total order using Byzantine fault tolerance, one of the best protocols known so far is BFT Smart, and we just compare performance in terms of throughput and latency, how fast you execute an operation and how many operations per second you can execute, and the difference is it's quite impressive. So that's all I can say about this. As takeaways, so asset transfers do not always require total order, and they might only require total order formally in the case where everybody can access the same account for debiting money, which I would argue is a rare case. Yeah, usually you have holders which are bounded compared to this whole system size. In fact, for what you need mostly is some kind of a source order, some causality order, causal, partial, some weak partial order using causality. Yeah, so you can do it asynchronously, which is an advantage because, as we know, at least some of us know that consensus does require some synchrony to be implemented. It's not only expensive in terms of bandwidth, it's also it requires some strong assumptions about synchrony. What I said, limited scope smart contracts, what I mean here is a subset of processes who can execute operations, critical operations on the same part of the state, but again, it doesn't mean that everybody should agree on the order of these operations. Only these guys should be able to agree. So essentially, the account owners need consensus among themselves, but not globally. And well, as I promised, well, we have some coming probabilistic implementation of this data structure, asset transfer, using some underlying probabilistic secure broadcast algorithm. Okay. And I think I will stop here, and I will take your questions if you have any.